I'm going to have a look at the PTC touch peripheral on the AVRs. It's a very good touch solution, giving high levels of robustness against noise, water tolerance, and yet it's so simple to set up and get working. I'm going to base this on some standard hardware. This is the one you might expect to choose for such a job. It's the 327, the tiny 327 with the PTC peripheral. This is one of the standard demo boards with touch buttons built into it. My own preference is to use this little board, which is a Curiosity Nano. Same chip, it's got a built-in programmer, debugger, and it's very small in form factor. So that enables you to build this into smaller products for prototyping touch features. So we're going to set this up in Atmel Studio using Atmel Start. And when you plug the Curiosity Nano into the PC, it brings up this page, the start page for the Curiosity Nano, giving all of the data sheets, user guides, and useful stuff. We're not going to use that. We're going to go straight into Atmel Start, a new project, create new project. And we'll set up our device, which is the AT Tiny 3217. We're using the F part. And we have the basis of our new project. Okay, we're going to add some software components. First of all, we need a middleware, which is our QTouch library. Add component. We'll set that up first before we add anything else. First thing to do is to open the configurator. We want to add a couple of buttons, so we'll add 2 self-cap buttons. That can be self-cap or it can be mutual capacitance. Mutual can be very good if you want to look at water tolerance. We're going to keep it simple. 2 self-cap buttons and add those in. It'll create them. And first thing it's going to say is we're going to optimize the clock frequency of the chip for touch. So say, you happy for us to do that? Yes, we are. It's going to basically run it at full speed. That's what our notification is, just that we've set up the clock for you. So we've got 2 sensors here. We're going to allocate those to some pins. We're quite happy with the ones it's chosen, PA4, PA5. The other thing we are going to add is a driven shield. Driven shield is an area like a ground plane, but it's actually call it a guard plane, which allows you to protect or decouple your buttons from the environment around it. You may have motors and noisy stuff going on. The driven shield allows you to eliminate a lot of that noise, so we're going to add that in as well. Let's put it on PA6, so those pins are fairly close to each other on our board, so we'll go along with that. Happy with that. On the parameters, you're able to set up certain things here, like the clock that the PTC is driven at. We're quite happy with the frequency it chooses. It'll choose the optimal clock. Some other things like number of oversamples taken on each sample, 16 times oversampling. That's like a way of filtering out noise. You've got 2 types of gain, digital and analog gain. They've defaulted to 1, which is quite a low gain. The amount of delta or signal deflection you see from our results when you touch the button is going to be set by those. Now we can set them up now if we have an idea what we want, or you can go into one of the header files later and tweak those should you need to make changes. I never normally change this stuff. It's normally optimal from the beginning, so for right now we'll leave everything where it is. I'm going to keep this simple. Pins are set up, parameters are set up. We're quite happy with that. One other thing that we might want to do here is when you're tuning the product, when you're tuning your touch, you can have a data connection. Now this is something we'll stream into Data Visualizer. I normally like to take control of the UART myself rather than let the touch routine do that. So I normally disable that. I don't use the built-in one. So I'm going to go back to our dashboard and I'm going to add another software component, and I want to add my own UART driver, which I can use with my own software. Add that component, just set that up briefly. That's going on PB3, PB2, which are fine, they're default for the board. Clock's full speed. I'm going to let's increase the frequency, the baud rate. Okay. We don't want any of the fancy stuff like printf support. It tends to be very useful and nice to use, but it is very large. I keep things simple and I send bytes and stuff to the UART myself, old school. So we'll leave that where it is, and that should be about it. Oh, there's one other thing we might want to play with, is that on the Nano board we have some other functions which are useful, an LED and a push button. We can add both of those on as well. It's useful to see immediate feedback when you're touching the buttons to see that they're working. LEDs on PA3, push buttons on PB7, so we'll add those into our setup as well. So back to the PinMux, PA3, we've got our LED, set that as an output. On the schematic, I think it was active low. Yeah, so it's driven low from BDD, so we will set that as active low, so it defaults to high. And the switch was on PB7. PB7 is there, so switch note, it's a digital input. Yeah, we will add a configuration to that. We'll give it a pull-up resistor. Okay, so that's pretty much everything we're going to need to get this up and running. So generate project. We're going to put this into our curiosity folder and we'll call it 3217 test. Okay. So here we have our project generated. Can have a look at some of the code that's been created. Here's our main file, not too much in it at the moment. Some of the interesting files you might want to look at is the touch.h under the library. Under touch.h, remember some of the parameters we set up in Atmel start configuration. Here we've got access to the analog gain, the digital gain and filter levels, so you can change these values in the header file, recompile and run immediately without going through all of the Atmel start again. So that's quite a useful file to have a play with. The APIs are probably the other thing you'll want to look at. Here you've got the actual APIs that you call from your application. One I use is the get sensor node signal. This basically returns the raw value of the sensor node. Rather than use the button is touched, button isn't touched, Boolean type feedback, I like to have a look at the actual analog data coming from the touch process. So that's a very useful one to use in the touch API PTC.h. Now to start using these we need to head back to our main.c. Before you set anything up, the first thing the touch application needs, it needs this command called touch process. There it is, which basically says go and refresh all of the touch nodes, the touch sensors, and report back latest data. So run that in your acquisition loop to get live data back. Next I'm going to add the get sensor node signals, so get sensor node, so get sensor node signal, that's the one. Going to add that twice for 2 sensors, basically node 0 and 1, keep it nice and simple. We need a couple of variables to stick those into, so let's create sensor 0 and sensor 1. So that's the basic touch code needed. Once you've got that data into send 0 and send 1, then we've got everything we need to start processing touch. Everything else is just making this bit work. So we need to obviously define these variables. So I'll just set these up very quickly with a cut and paste. The other thing I'm going to add in is delays, just to make my timings work. So you might want to include the delay header file. And once I've received my data, do something with it, analyze it, and then act depending on whether the button's touched or not. I need to have a bit of code to process that. So I've got a few more variables to play with. We always have. I've got my sensor 0 and 1. I'm going to set some baseline levels so I know what the delta level is when it's been touched. So I need to set up a baseline value. So that's basically, so all I'm going to do is when my delta is above a certain threshold, I fix that at 50 in my code for button 1 and button 2, button 0 and button 1. Then I light an LED. If it's not touched, then the LED doesn't light. So very simple code. Let's set up the baseline values. Nothing too complicated here. I'm going through a loop. Flash the LED 10 times at startup, and during that I'm going to again run my touch process and write the level to the baseline. I like to do this several times because at startup there's sometimes some unknown levels lurking about as things stabilize, so get 10 writes in there. By the end of it, you know you're getting good stable data into baseline 0 and baseline 1, and that is basically the code. Next we're going to have to set up our hardware, so we go to the tools, the device programming, have a look what it's using. Tool for programming, this is our Curiosity Nano board. We're going to apply that, read in the signature and the voltage. It runs at 3.3 volts by a standard. So we've got hardware set up. Let's try and build and run it and see what happens. Well, that all seems to be good. So we know that the Curiosity Nano and our code are working fine. So we need to set up some touch hardware. I did a speeded up video of touch button fabrication using an old piece of FR4 and some copper tape. Single-sided FR4, so I'm going to use that as the guard plane underneath. The copper button's going to stick on top. And the buttons are about the size of a fingertip, ideally, so when you're touching the button, most of the copper is covered with the finger and not left open. Smooth down the buttons, make sure they're nice and flat so that when you place the plastic over the top, the acrylic, then you're not going to have any air gap between the copper and the plastic. That's crucial for getting good sensitivity. The wire uses a very thin gauge wire, again trying to minimize the amount of copper between the sensor and the microcontroller. The less copper you have, the more sensitive the button will be. Use a double-sided tape for securing the fascia, the acrylic. This is the one without the plastic in between the adhesives. It's just adhesive and no substrate plastic. Connect up the driven shield on the back, and you can see that guard plane. We have 3 connections, 2 to the button, 1 to the driven shield. Secure the board in place, and then finally make the solder connections to the Curiosity board. Very, very simple touch button assembly, but as you can see, the results are fine. Getting good sensitivity, LED lights just as the finger touches the button, with a threshold of about 50. Now, as I mentioned earlier, I do like to have a look at the analog data. I like to see what's going on with the signal levels, just to be sure I've got good design and good setup mechanically as well as in software. So I'm going to add some other code in now, some functions, basically just for writing to the UART, sending data out on the UART, and allowing me to look on a terminal program such as TerraTerm, one of my favorite, to be able to analyze that data. So here are the functions, very simple. Got a function print char just for writing to the UART. Send int, which allows me to send integer. I've also got send char and carriage return line feed, which is just to keep the screen tidy. This is the main one I use, send int. Takes in an integer value, and all it does is strip the number down, so into tens of thousands, thousands, hundreds, and so on, and makes each value, each digit, into an ASCII character. So I'm adding 30 onto it basically, and then sending it out to the UART just to make it printable. Nothing too clever, but it works fine. And in this way I can send an integer straight to that function, and it will appear on my TerraTerm terminal. So I'll add in the prototypes, and that should be good to go. And then add in my code for sending out the data into my acquisition loop. So here I'm sending out the raw data from sensor note and the baseline value, same for sensor 1, and then doing a carriage return. I'm printing a space in between each of them just for clarity. Let's build. And now we can have a look at that raw data. As we're touching the buttons. Button 1, we're seeing a delta from about 516 to about 610. Button 2, we're seeing a delta of 516 up to about 611, something like that.